Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 5 on factoring polynomials. Now up to this point in time, we've spent a lot of time, maybe too much time, on looking at how to multiply two polynomials together. All right? In this lesson, we literally start to do almost the opposite of that, which is to take something that is a product and rewrite it in the form of a product, something that is the end result, and rewrite it as the form of a product. So let's jump into that right now. Now you've seen factoring throughout the years, okay? You certainly saw it last year and the year before, but let's really kind of boil it down, right? The word factor has two meanings. So factoring an expression is an extremely important skill in algebra, and the word factor has two distinctly different and important meanings. So let's kind of like take a look at those. The first one is the verb factor, and all that means is to rewrite an algebraic expression as an equivalent product. That's all it is, right? And you've been factoring numbers for years, right? When I write something like 8 as 2 times 4, I have factored the number 8. When I take the number 15 and I say, well, that's 5 times 3, I have factored the number 15. Now, the other word that's associated with factor is factor a noun, and that's an algebraic expression that's one part of a larger factored expression. So for instance, if I took the number 15 and I factored it as 3 times 5, I would say that 3 is a factor of 15 and 5 is a factor of 15. And so it's kind of weird because those words are the same, right? But one of them is a verb, it's an action, it's to do something, and the other one is a noun, it's part of it, right? So let's get into exercise number 1, where we look at a binomial expression and how to factor it. Consider the binomial expression 6x squared plus 15x. Letter A. Write the individual terms 6x squared and 15x as completely factored expressions. Determine their greatest common factor. All right, so here's what I mean by that, right? 6x squared. Well, the number 6 can be written as 2 times 3. And I can't break that down any more than that. It's 2 times 3. And x squared can be written as x times x. So literally 6x squared, factored all the way out, is 2 times 3 times x times x. Now 15x, right, the number 15, can be factored as 5 times 3. And of course, the variable x can't be factored anymore at all. So that's 5 times 3 times x. So you've worked with GCFs before, but now they're going to become very, very important for us. What is the greatest common factor? Now it's factor the noun, right? What is the greatest common factor? Well, when I look at these two, I see that both of them contain a 3 times x. So the greatest common factor is 3x. Now let's talk about GCFs, because although this is one great way of figuring out what the GCF of two terms are, it's somewhat inefficient, right? So when I'm thinking about GCFs, and we'll get to letter B in a moment, what I want to do is I want to look at the coefficients that are involved, and I want to say, what is the largest number that divides into both 6 and 15? And the largest number that divides into both 6 and 15, divides into is another word for factor, right, is the number 3. It's the biggest number that goes into both of them. And then I think about the variables. Here I have an x squared, and here I have an x to the first. There is literally an x to the first that sits within an x squared, so that is also a common factor. So 3 times x is the greatest common factor. Now let's look at letter B. Using the distributive property, rewrite 6x squared plus 15x as a product involving the GCF from A with another binomial. Okay, so here's what I'm getting at, right? 6x squared plus 15x can be thought of as 3x times 2x plus 3x times 5. Notice, right, that common factor. That means I can take that 3x and then write it like this. right? Now you might say to yourself, well, wait a second, that's not using the distributive property. The distributive property says when you have something out here, you can multiply it through here. And I don't disagree with you, but what the distributive property really says is that these two things are the same. And if I can multiply the 3x through, I can also sort of take the 3x back out, right? Oftentimes we say we factor out a g.c.f. because even though there's the 3x is in this term and this term, then when I take it out going sort of the opposite direction of the distributive property, it's sitting outside of the parentheses. Let's take a look at letter C because we definitely want to make sure that we never forget a very important thing about algebraic manipulation. Let's take a look. Evaluate both 6x squared plus 15x and the factored expression you wrote in B for x equals 2. What do you find? What does this support about the two expressions? All right, well, let's go ahead and go through this together. I want to take x equals 2, and x equals 2 is just a random value of x. We could have really used anything. But I want to take x equals 2, and I want to put it into this expression, figure out what it's equal to, evaluate it. Then I want to take x equals 2 and put it into this expression and figure out what it's equal to. Let's do this together. All right, so first things first, 6x squared plus 15x. All right, I just put a line underneath here. All right, so I'm going to have 6 times 2 squared plus 15 times 2, right? Now 6 times 2 squared is going to be 6 times 4, and 15 times 2 is going to be 30. 6 times 4 is 24 plus 30, and that's equal to 54. So my original expression is equal to 54 when x is equal to 2. Now let's take a look at my factored expression, which is right up here. 3x times 2x plus 5. All right, well, what's that equal to when x is equal to 2? Well, that's going to be 3 times 2 times 2 times 2 plus 5. All right, just be careful here. That's going to be 3 times 2 times 4 plus 5. And that's going to be 3 times 2 times 9. And now we'll just do 3 times 2 and get 6 times 9. And 6 times 9 is 54. All right. Now notice when I evaluate this expression and this expression, I mean, the steps, right, the arithmetic, all of that, very, very different. And yet, they both come out to be 54 at the end. And this reinforces something that I absolutely hope that you understand. These two expressions are equivalent. These two expressions are equivalent. 3 exclamation points are needed. All right. The reason that it's so important to understand this is that when we manipulate algebraic expressions, we're almost always doing it for a reason. There's a mindful manipulation going on, okay? But at the end of the day, wherever this expression shows up, I could put this expression because they're the same expression. They are equivalent. And two equivalent expressions can always interchange for each other. Much of the algebra that we do, a lot of algebra we do that students think we're doing because we're solving an equation or something like that, is really just replacing one algebraic expression with another one that is equivalent to it. So never ever forget that. That being said, let's keep working on factoring. All right, now it's important to become fluent reversing the distributive property in order to factor out a common factor. Now, most of the time when we factor out a common factor, we're looking to factor out the greatest common factor. Not always, but most of the time, all right? Now, in order to do that, we've got to be able to identify the greatest common factor of 2 or more terms. So that's what we're going to get some practice on in exercise number 2. Let's take a look. For each of the following sets of monomials, identify the greatest common factor of each. Write each term as an extended product if necessary. Okay, so again, I'm going to do this on a few of them, but then I'm hoping that we can kind of develop some patterns and figure out what the GCFs are without doing that. So let's take a look at 12x cubed and 18x. Okay, I'm going to write them out in their fully factored glory, and then we're going to figure out what the greatest common factor is based on that. So 12 is actually kind of an interesting number because it's 4 times 3, and then 4 is 2 times 2. So 12x cubed is going to be 2 times 2 times 3 times x times x times x, right? So 12 is 2 times 2 times 3, and there's nothing we can do to factor that anymore because 2, 2, and 3 are all prime numbers. That's as good as we can do. Now 18x, that's 2 times 9, and 9 is 3 times 3, so that's going to be 18x is going to be 2 times 3 times 3 times x. All right? 2 times 3 is 6 times 3 is 18 times x. So what's the greatest common factor? Well, they contain a 2, a 3, an x, a 2, a 3, and an x. So the greatest common factor, which I need to kind of put down here, is 2 times 3, which is 6, and then x. 6x. Now again, how do we do this more quickly? Well, we say to ourselves 12 and 18. What is the largest number that goes into both? Well, 2 goes into both, 3 goes into both, 6 goes into both, and 6 is the largest one that will divide both 12 and 18 nicely, so that's part of our greatest common factor. Notice this one has an x cubed and this one has an x to the first, so the most x that can be common to both of them is x to the first. So our GCF is 6x. Let's take a look at letter B and do that one together. For letter B, we have 5x to the fourth and 25x squared. All right. Well, 5x to the fourth, that one's easy, right? 5x to the fourth is 5x, x, x, and x. 25x squared is 5, so this is 5x to the fourth. And 25x squared, don't want you to think they're the same, is 5 times x times x. Right? So what is common to both of them? Well, obviously a single 5 is common to both of them, as are 2 x's. Right? So I have a 5 times x, which is common to both of these, and therefore the GCF is 5x squared. Now again, let's kind of think about this in terms of our sort of shortcut methods so that we don't have to write them out like this every time. Can you write them out like this every time? Absolutely. But it's going to take you a while and eventually you're not going to want to do it. So how do I figure out the GCF? I look at my 5 and my 25 and I say, what is the largest number that divides into both 5 and 25? That happens to be the number 5. That's not unusual. Oftentimes the GCF in terms of the number could be one of these two. Now this one is an x to the fourth and this one is an x to the second, and notice it's the x to the second that is part of the GCF because there is an x to the second sitting inside of an x to the fourth. I mean, there it is, x times x times x times x, and there's our x to the second. All right, so we can always do it that way, and in fact, let's take a look at letter C and think about how to do this using our shortcut method as opposed to writing everything out. Let's take a look at letter C. Here we have 21x squared y to the fifth and 14x to the first y to the seventh. Very, very important in that second one to realize that's x to the first and y to the seventh, not x times y, both raised to the seventh. All right, so the first thing I'm going to do is I'm going to think about my 21 and my 14 and what the largest number is that divides into both 21 and 14. That's probably pretty obvious. The biggest number that divides into both 21 and 14 will be 7. All right, now we think about our x's. We have x to the second and we have x to the first, all right? The largest x power that resides in both of those is x to the first, not x to the second, right? Because this one doesn't have an x to the second in it. So we just have x to the first. All right. Now we have y to the fifth here and y to the seventh here. Y to the fifth and y to the seventh. the largest power of y that is contained in both of those is y to the fifth, right? There is a y to the fifth in here. It's y to the fifth times y to the second. So we just have y to the fifth. So our GCF in this case, 7x to the first, y to the fifth. All right, now it doesn't make any difference whether there are 3 terms or 2 terms, you do it the same way. So let's take a look at D together, and then I'll have you work on E and F on your own. So letter D. Here we have 24x to the third, 16x to the second, and 8x to the first. All right, so the first thing I do is I look at 24, 16, and 8, and I think, what is the largest number that divides into 24, 16, and 8, and that happens to be 8, right? So I begin by saying, well, my GCF has to include 8. Excellent, right? Then I look at x to the third, x to the second, and x to the first and say, well, what is the largest power that every one of those terms contains? And that's x to the first, right? This one has an x to the first, that one certainly has an x to the first inside of it, and so does that. And so my GCF is 8x. Now, if you're starting to figure out that the variable portion of the GCF is simply the smallest power of the variable that's present, well, you're totally right, okay? So, right, I mean, x to the first, x to the second, x to the third, there's an x to the first there it is. All right, what I'd like you to do is pause the video now, think about letter E and letter F, and try to come up with the GCF for each of those. All right, so in letter E, we've got 20x to the third, negative 12x squared, and 28x. That negative attached to the 12 is really no big deal, all right? There will be a problem later on in this lesson where maybe I want to take the negative into account, but for right now, I don't need to really worry about it. I've got 20, negative 12, and 28. The largest number that divides into 20, negative 12, and 28 is 4. All right? Then I have an x to the third, an x to the second, and an x to the first, and that means, at best, I can do an x to the first. So my GCF there is simply 4x to the first. In letter F, I've got 18x squared y squared, 45x squared y, and 90xy squared. Lots going on here, lots going on, but still pretty easy, right? I think about my 18, my 45, and my 90. The largest number that divides into all 3 of those, the largest numerical factor of all 3 of those, is going to be 9, right? 9 divides into 18, 9 divides into 45, and 9 divides into 90. All right, now let's tackle my x's. I've got x squared, I've got another x squared, and I've got an x to the first, right? The biggest power of x that I can possibly have in each one of those is x to the first, right? Then I have a y squared, a y to the first, and another y squared, and the biggest power of y again that sits inside of each one of those terms is y to the first. So my GCF is 9xy, okay? Now, most of the time in this course, you won't have to worry about real craziness like this. You know, the most you probably would ever have to do on something like that is in a multiple choice problem. Given those 3 terms, you got to be able to identify their GCF. But now we want to be able to identify the GCF in order to factor binomials and trinomials. So let's take a look at some of that. Here we go. Once you've identified the greatest common factor of all terms of a polynomial, you can use the distributive property in reverse, I guess, I don't know, maybe, or maybe it's just the distributive property, to write it in factored form. All right, so let's take a look at exercise number 3. Write each polynomial below as a factored expression involving the greatest common factor of the polynomial. All right, here we go. So in letter A, we've got 6x squared plus 10x. Right? What I want to do is I want to identify the GCF and then write the polynomial as a factored expression involving that GCF. So let's identify the GCF first, right? I think about the 6 and the 10, and the biggest number that divides into both of those, whoopsie, is 2. And then I think about my x squared and my x to the first. The best I can do there is 2x. So my GCF is 2x. All right. That means I can now take my binomial and rewrite it as 2x times something. All right. Now, what do I have to multiply 2x by in here to get this as the result? That's what I mean by running the distributive property in reverse. I'm literally thinking about what would I multiply 2x by to get 6x squared plus 10x? Well, first, what would I multiply 2 by to get 6? Well, that would be 3. What would I multiply x by to get x squared? Well, that would just be x. Then my plus comes along for the ride. It's not like that's going to change to minus right now. Now I think, well, what would I multiply 2 by to get 10? And that would be 5. And the x comes along for the ride, right? 2x times 5 is 10x. All right. You can check every factoring problem ever. Let me just kind of get rid of this so we can see it a little bit better. You can check every factoring problem ever by multiplying it back out to see if you get what you started with, right? Remember, this and this should be equivalent, right? You should really never miss a factoring problem as long as you're willing to think about, if I multiplied through by 2x, would I get back to here? So one common mistake that occurs in something like this that I've seen a million times as a math teacher is somebody will write down 2x, they'll write down 3x, and then they'll say 3x plus 5x, which is weird because 3x plus 5x would be 8x, and then you'd get 2x times 8x, which is 16x squared. But even if you said 3x plus 5x and then you thought about multiplying the 2x back through, then 2x times 5x would be 10x squared, not 10x to the first. All right, let's do one that's very simple. 3x minus 24. That's one that you've probably done in previous grades, right? First, the GCF. I look at 3, I look at 24. The biggest number that divides into both of them is 3. And since the 24 doesn't have an x on it, there is no variable in the GCF. I can now say that 3x minus 24 is equal to 3 times, let's see, it would have to be x, right? And then it would have to be minus 8. 3 times x minus 8 is the same as 3x minus 24. All right, now, side note, if you've never seen the purpose of factoring or why you do it, I promise you, in this course, we will see the reason why we factor. All right, we will use factoring to solve a variety of different problems, especially in the next unit. For now, it's just a skill we want to get good at. Let's do one more of them together and then we'll have you do some of them on your own. Right here, we've got 10x to the second minus 15x, a little bit small for me to see. 10x to the second minus 15x. So let's first identify the GCF. All right, so from 10 and 15, we can get a 5 from both of those. From x squared and x to the first, we can get an x. All right. We can now factor this thing and say that that's going to be equal to 5x times, well, I'd have to have 2 times 5 was 10. X times x is x squared. And then 5x times negative 3 is negative 15x. And that would be our factorization. All right. Really, really kind of cool. Now again, it doesn't really matter whether you start with a binomial or a trinomial or whatever, right? You just have to be able to identify the GCF and then write the polynomial in its factored form. Let's do a trinomial one together. We've got here 4x squared plus 8x plus 24. All right, this is a very, very common one. I look at 4, 8, and 24, and I can see that the biggest number that divides into each one of them is the number 4. All right, so that's part of the GCF. Notice that the 24 doesn't have a variable on it. If there's even a single term that lacks the variable, then the variable is not part of the GCF. All right, so here, the GCF is simply equal to 4. And that means we can rewrite the polynomial as 4 times something. What do I multiply it by? Well, 4 times x squared would be 4x squared. 4 times 2x would be 8x, and 4 times 6 would be 24. right? So just simply 4 times x squared plus 2x plus 6. All right, let's do one more of them together and then have you do a few of them on your own. Let's take a look at letter E. Here we have x to the third minus 5x squared plus 2x. Now keep in mind, right, that really the coefficient on that x cubed is the number 1, right? So if I think about 1, 5, and 2, there is no number that divides into 1, 5, and 2, no whole number that is, that divides into 1, 5, and 2 other than the number 1. So in terms of the g.c.f, there is no number portion of it. On the other hand, I have an x cubed, an x squared, and an x to the first, so there is an x in each one of those. And in fact, the g.c.f is just x to the first. That means when I factor it, I can say it's x times x squared minus 5x plus 2. And that's it. All right, what I'd like you to do is pause the video now and see if you can work through the last 4 of these things, and then we'll go through each one of them. All right, so letter F, we've got 10x to the third minus 35x squared. All right, this is a nice one because it's got both a numerical component and a variable component to the g.c.f. Hopefully it's obvious the biggest number that divides into both 10 and 35 is 5. Then we have an x to the third and an x to the second, so the biggest power of x that sits inside of both of those is x squared. So our g.c.f in this case is 5x squared. That means I can rewrite this as 5x squared times what? Well, 5 times 2 is 10, and x times x squared is x cubed. Now, 5 times negative 7 is negative 35, and the x squared again just comes along for the ride because we've already factored it out. So 5x squared times 2x minus 7. All right, let's keep working on this. Right, we've got 3 more of them left. Let's take a look at letter G. Here we've got 10x squared minus 40x minus 50. When we think about the numbers 10, 40, and 50, the largest number that divides into all 3 of those is the number 10. And again, because we've got an x squared and an x to the first, but no x attached to that constant, attached to that 50, there is absolutely no variable that's part of the g.c.f. There's no variable that we can factor out. So the g.c.f here is equal to 10, which means this trinomial now can be written as 10 times x squared minus 4x minus 5. 10 times x squared minus 4x minus 5. All right, let's take a look at h. Nice little binomial there. We have 8x to the fourth minus 2x squared. This one's a little bit tricky, okay? The 8 and the 2 are easy, right? The largest number that goes into both of those is 2. All right. The x squared and the x to the fourth, also easy, right? The sort of the power that's sitting inside of both of those is x squared. So, right, our g.c.f is 2x squared. That means we can rewrite this thing as 2x squared times, well, let's see. What times 2 gives me 8? Well, 4. What times x squared gives me x to the fourth? Well, another x squared. Now, what times 2x squared gives me negative 2x squared? Well, that would be negative 1. All right, that is where a lot of students will make a mistake. They'll say, well, all right, I factored the 2x squared out. So a lot of students will just write down the answer as 2x squared times 4x squared. The problem there is if you multiplied 2x squared times 4x squared, you'd get your 8x to the fourth, but you'd never end up with this term, right? So this and this wouldn't be equivalent. And remember, we're not just doing something to do it. We're not just doing something to manipulate some kind of an expression. We are producing 2 expressions that are equivalent to each other. So if you use the distributive property here and you don't get back to where you began, then you either did the distributive property wrong or you made a mistake in your factoring. All right, last one. Let's take a look at this one. 8x cubed plus 24x squared minus 32x. All right, first let's tackle the numbers. 8, 24, and 32. The largest number that divides into all 3 of those is the number 8. Awesome. Then we have x cubed, x squared, and x to the first. so there's an x to the first in each one of them. Therefore, our GCF is 8x. And this entire trinomial, I'll write it down here, can be written as 8x times, let's take a look. Well, what times 8x would give us 8x cubed? Well, just x squared, right? X squared times x is x cubed. What times 8 gives me 24? Well, that would be 3. Then I'd have to have a 3x, so that 3x times 8x gives me 24x squared. And then what times 8 will give me a negative 32? That will be a negative 4, and the x has already been factored out. 8x times x squared plus 3x minus 4. Really critical to be able to do this skill. There are many different types of factoring. The easiest and most basic of them all is factoring out a GCF. So let's keep working with factoring out a GCF. Now, sometimes the greatest common factor of an expression will be a binomial instead of a monomial. Strangely enough, these are sometimes easier for students to do because they're reasonably easy to spot. Let's take a look at exercise number 4. Rewrite each of the following expressions as the product of two binomials by factoring out a common binomial factor. Letter A, x plus 5 times x minus 1 plus x plus 5 times 2x minus 3. All right, so this is actually kind of cool, right? Because we can literally see what is common in this expression. Now really, keep in mind, we got something times something plus something times something. That x plus 5 is your GCF, right? A GCF of x plus 5. So if I then take this down here and I factor my x plus 5 out, what does it look like inside of the parentheses? Well, it looks like x minus 1 plus 2x minus 3. Now, that's pretty good. It's not done because it says rewrite the following expressions as the product of two binomials. Well, here's one binomial, but now I can simplify what's inside of here. Now keep in mind, I'm just adding two binomials together. So I can use the associative and commutative property of addition and just get rid of those parentheses. And now say that's x plus 5 times x minus 1 plus 2x minus 3. And now I can combine like terms inside of this parentheses. X plus 2x is 3x. Negative 1, negative 3 is negative 4. And there we have it. X plus 5 times 3x minus 4. Now this one's going to be a little bit trickier because of that subtraction. I'd like you to pause the video now and see if you can do this. And by the way, if this skill seems vaguely familiar, it's because we did it way back in Unit 1. So you have seen this before. It's okay if you've forgotten. That's a long time ago, Unit 1. We're already into Unit 7. But see if you can figure out what this one's going to be. Just be careful of that subtraction. Pause the video now and see if you can work through it. All right, in this case, our GCF is 2x minus 1. Right? GCF is 2x minus 1. So I'm going to rewrite this entire expression as 2x minus 1 times 2x plus 7 minus x minus 3. All right. Now let's talk about why that subtraction is so dangerous, so to speak. Right, the subtraction is dangerous because, you know, these parentheses, whatever, they're really not doing anything. I can just sort of get rid of them. But I really have to change this into adding the opposite, right? So instead of subtracting an x minus 3, I'm going to add a negative x plus 3. A lot of teachers will say I'm either distributing the subtraction or I'm distributing multiplication by negative 1. So I could really think about this as sort of like a negative 1 that I'm multiplying through that parentheses by. That's absolutely key, all right? Because a lot of students will just do 7 minus 3 and get 4, but you don't have that. You actually have 7 minus negative 3, which is 7 plus 3, which is 10, okay? Anyway, let me finish this one up now. That's going to be 2x minus 1. I then have 2x plus negative x. That's just going to be 1x. 7 plus 3 is 10. and I get 2x minus 1 times x plus 10. So if you got that one right, that's awesome, right? It means that you kind of have the general idea of what's going on here, plus you remember what to do when you subtract one polynomial from another one, which we didn't do all that long ago. That one we did just a few lessons ago. All right, let's do one more problem that's a little bit challenging. I love this one. Now, the structure of an expression should tell us what kind of manipulations we can and, in a certain sense, what we can't do. So let's look at exercise number 5. I like this problem. It's a fun one. If the binomial expression 3x plus 5 is equal to 9 for some value of x, determine the value of the expression shown below for the same value of x. Whew. All right. So I'd like you to manipulate this. Play around with this. Do whatever you can. All right. Don't try to figure out what the value of x is. That's not the point here. I know that 3x plus 5 is equal to 9 for some value of x. We could figure out what that is, but please don't. I then want to know what the value of this expression must be if I know that. Pause the video now and play around with mindful manipulation on this expression. All right. Well, there's nothing wrong actually with factoring part of an expression. Remember, I'm just replacing, equivalent things with equivalent things. So I'm going to, for a moment, just kind of ignore that plus 1. I don't have to worry about that. And I'm going to look at the fact that there's a 3x plus 5 and a 3x plus 5 sitting there. So I'm going to rewrite this by factoring that 3x plus 5 out of the first two terms. Right? And that's going to leave me with this, right? So I've got a 3x plus 5 times 3x and a 3x plus 5 times a 7. So I can rewrite that portion as 3x plus 5 times 3x plus 7 plus 1. All right, now keep in mind that I know 3x plus 5 is equal to 9, right? I know that. There it is. It's right there. So that's equal to 9. What would 3x plus 7 be? Well, keep in mind that 3x plus 7, right, is 3x plus 5 plus 2, right? So that's 3x plus 5 plus 2, and that's 9 plus 2. So 3x plus 7 must be equal to 11. It's got to be. If 3x plus 5 is equal to 9, 3x plus 7 must be just 2 larger. That's got to be equal to 11. So this entire expression is 9 times 11 plus 1, which is 99 plus 1. And that entire expression must be equal to 100. So if you got 100 on this, well done. Well done on your mindful manipulations, on understanding how to factor out a binomial expression, etc. All right, let's wrap this one up. So today we saw our first foray into factoring, and our next 3 lessons are going to be devoted to factoring because it is a very, very important skill. One can really think of factoring almost as reversing the multiplication process out to figure out, well, what 2 or 3 or however many things did I have to multiply together to get this result? And of course, that's harder than doing the multiplication itself because the multiplication itself is just a straightforward step 1, step 2, step 3 kind of thing. Factoring takes a little bit more work. Now, the factoring that we concentrated on today was identifying the greatest common factor of a given algebraic expression and then writing the algebraic expression in terms of a product using that g.c.f. We'll be using that quite a bit as we move on and as we see other types of factoring. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.